Hi, I'm Simon Pettersson, software consultant at 3Tech Technology. We hosted this event a month back, I guess. All right, I'll dive in. Who knows what this is? You can? I can tell you. This is ancient scripture or something like that. It's macros. And if you buy several million microprocessors, this is what they'll give you to base your type-safe, nice C++ code out of. And I like really old computers, which are like 30 years old. So I decided to try to make something better for one of these old computers, which is an Amiga 500. So these macros, since you can read them, what they do is they let you read and write to memory mapped hardware devices in the computer. And it's just like bit shifting and macros going on. So what if you can do something like this with const.expr? So you have this lookup table which works in compile time. You have an enum you can use to look up a register, and you can use read or write functions on this type, on this variable. And this read or write functions, they can check, they can do static analysis before you even reach runtime. So in order to build this, we need this. This is old, we got it 6 years ago with C++11, but it's really useful. This is code from a really big library, from a very big company. I'm not going to mention the name of it, but it's Google. You can rewrite it like this, just with this simple keyword, auto, which makes it like, what is it, like a third of the code? So should we use auto all the time, like everywhere where we can? Well, yeah, I guess. Like if you take this square function, for example, it doesn't care if it's 8 bits or 64 bits, or if it's bananas or apple. The only thing it cares about is that you can multiply this number with one of its own type. So this is gonna be like, it's gonna work for everything, which has the operator, like star, whatever it's called. And also it enables us to use lambdas. Who knows, who can tell me what a lambda is? Shoot. All right, no, it's just, it's a struct with a function, what is it called? Operator function call, right? Yeah, so it can contain state, and it has a type. In this case, when you use this lambda syntax, it's a generated type. So you can't really type it, so you need to use auto. And this is, of course, since you're C++ professionals, you knew all of this already. So why am I telling you this? Well, to do factories of lambdas, you need auto. It's essential. So imagine you have something like a lock. And this lock, you need the right key, and if you use the right key, it's going to return you a value. If you have the wrong key, it's going to return nothing. So you have this lock factory, make lock. It takes a key and a value, and it's going to return a lambda, which if you give it the correct key, it's going to return you a value. If you give it the wrong key, it's going to return you nothing. Is this clear? I guess. So you use it like this. You have a key, 42, you have a value, 1000 plus. You call the makeLock function, it's going to return you a lock. And you see the keyword to the left? It says const.expr, and that means you can do this in compile time. This doesn't even reach the platform you're targeting. Like it doesn't translate to assembler instructions, it just happens in the compiler. So you can do static assert since it's compile time. So if you call mylock with 84, which was the wrong key, the key was 42. So 84 would return nothing, and 42 would return like the value. All right. What if we have one key? We have the key, it's 42. And then we have like a big pile of locks. And then we want to find which lock does this key fit, and then we want to retrieve the value. And if there's no lock with containing, like matching the key, it's going to return you nothing. In this case, we need to construct like a tree of locks. So you arrange the locks in a tree structure. You have all the locks as leaves, and then you need something to connect it all. And for that, you use a branch. So this make branch factory function, it takes a left subtree and a right subtree. So the subtree could either be another branch or it could be one of these locks. So it's going to return another function which has the same signature as the lock. So the branch is going to return you another std optional, which could be either nothing or a value. And this function is going to first check the left subtree. If it returns a value, it's happy, it's going to return you the value. If it doesn't, it's going to recurse into the right subtree. If you put some makeup on this, because that's pretty easy, but to make it usable, it gets kind of hairy, at least for me. I'm not like the best programmer in the world. So you could end up with something like this. So you have a lookup factory. You pass it this, you have another map factory which produces these values, the locks. This is like the make lock function basically. And you map, in this case, A to 13, B to 55, C to 87. And then you can perform lookups using the square bracket operator thingy. And then you can use it in compile time. So you can make a native array of 55 items, like in this case. So going back to the Amiga. The Amiga has a 24-bit address space. And then it has restrictions on all these registers. So some registers you can only read. If you try to write to it, it's going to crash. And some registers you can only write, so it's going to crash if you try to read. And with macros, you can really, you have to just do the correct thing all the time. If you use C++ 17 type safety and all this jazz, it's gonna crash in compile time instead. So we map this. The register is an enum. So each one of these are named. I think PRA is something like the mouse button input or something. It's a byte. So you tell it, well, this is a register. It has this address. It's 1 byte wide, and you can read from it. So you can't write. And you construct this lookup table in compile time. Then you can use the read function. Since all of this information in the register fits in one 32-bit integer, you can typecast it to a 32-bit integer, and you can pass it as a type parameter to the read function. And then the read function is going to do static assertions. So it's going to see, well, can I read from this? Well, if you can, then it's good. Otherwise, you're going to get a compiler error. And then it's going to check the width. And I noticed a bug in this slide because it's going to try to read along from this byte register. So in this case, the compiler would throw an error in this second static assert. But if it's all good, it's going to get that address from memory, and it's going to return the value. So then you can compare. So the bottom section is what you get from the manufacturers of microchips with the macros. And the top one is, well, I wouldn't say, yeah, it's the same code, but in C++ 17. And this has like no overhead at all. So I didn't keep time, but this was if I had time over, I would show this. So this is the compiler explorer. What?
There is time over.
Is it time over?
Time over. Now you can speak.
All right. I'll just show this. So we create a lookup table. It has one item. It maps the integer 1 to the integer 42. If you look at the assembly code, well, it returns 42, which was expected.
Bigger, please.
Can I? Like this? Yeah. Perfect. So if we try to look up another value, like 2, oh, it's going to throw an exception. And this is like a lot of code for nothing. Okay, what about now? It's going to give you a compiler error. And if we look at the error, it's going to say something about, okay, this is too inconvenient, so I'm just going to talk about it. So what's happening is that there's a throw inside of one of in the lookup function. It throws an exception based on some criteria. And in compile time, if we look up the value 1, it's going to compile. But if we look up the value 2, it's going to reach a branch where you throw an exception. And in compile time, you can't throw exceptions because it's not runtime. So then it's going to crash saying something like, oh, you can't throw exceptions because this is runtime. You're stupid. Yeah. So this is a small library I wrote. Like I think it's 60 lines minus the license or something. So it's really tiny. And it's here, CMap. And this is the Amiga BSP example I made using the CMap library. And that's it. Thank you.